Hello students, welcome to Wondercom. This is in continuation of my previous video on electronic configurations of different elements and how these elements are being arranged in periods and groups in a periodic table. I have already discussed the elements of first three periods in my last video. In case you have not watched that video, you please go to the description box for the detailed links of that video. So let us move to the elements of the fourth period in the periodic table, where the principal quantum number is 4 and the period starts with the element potassium and ended with the krypton. The filling of electrons in the elements of fourth period is very important and to understand, because we can assume as usual that the electrons would move to the fourth orbit. So n is equal to 4, but in fact first two electrons go to this fourth orbit, fill this fourth orbit, but the next added electrons move to the third orbit. For an example, in case of potassium with the number 19 atomic number, so first orbit is a 2, 8, fourth orbit, 1 electron will go to the fourth orbit. Similarly, for calcium with the atomic number 20, 2, 8, 8, 2, but the next with the scandium 21, it will be like 2. See, this added electron moves to third orbit, and this train continues from scandium to your zinc with atomic number 30. So where these electrons, this should remain same, but the electrons will add here. Okay, so and this is based on the concept of energy associated with the energy label or the shells, or we can say now orbitals. That we can understand in a better way from AUFBAU principle for the arrangement or the sequences of atomic orbitals according to their energies. So let us have a look of this principle and arrangement. And this is the arrangement of the atomic orbitals on the basis of their energies. The added electrons are filled up in the elements according to these sequences, and this is the box diagrams for different atomic orbitals where the electrons can be filled up. Now let us have a look into the electronic configurations of the elements of that period. Here you can see the atomic numbers of the elements and their electronic configurations, which starts with the filling up of 4s orbital, which is filled up by the 2 electrons of the first two elements, potassium and calcium respectively. And then the added electrons are moving to d orbitals or 3d orbitals instead of 4p orbitals from scandium to zinc with atomic number 21 to 30. And then the 4p orbitals are being filled up by the remaining 6 elements from gallium to krypton. Here these 3d orbitals are energetically favorable than 4p orbitals as per AUFBAU principle, and these 10 elements are known as 3d transition elements. However, there are 2 exceptions in these elements, in chromium as well as in copper, where the AUFBAU principle is deviated, and in both the cases you would see 4s1 instead of 4s2. This is because in chromium 3d5 is exactly half filled and would be more stable than 3d4. Similarly, in copper 3d10 is completely filled orbital, so more stable than 3d9. Now let's move to the elements of 5th, 6th and 7th periods of the periodic table. The 5th period starts with the element rubidium, then strontium, yttrium, then zirconium up to xenon from the atomic number 37 to 54. And the general electronic configuration of this period is ns0 to 2, n-1, d1 to 10, np 1 to 6, and n is equal to 5. The filling of orbital starts from 5s with the elements rubidium and strontium. And then the added electrons move to 4d orbitals for the next 10 elements from yttrium to cadmium. and known as 4D transition metal elements. After filling of 4D orbitals, the added electrons then move to 5p orbitals from the elements indium to xenon. Just have a look into the electronic configuration of 4D elements, where you can observe the shifting of electrons from 5s to 4d orbitals in many elements like niobium, molybdenum, technetium, ruthenium and so on. And in palladium you see there is no 5s electrons at all. We know such type of deviations are due to more stable half filled or completely filled d orbitals. But here such deviations might be due to electron repulsion from 5s electrons, which would push the other electron from 5s to 4d. At higher energy levels, the orbitals are degenerated. That is, they have very close energies and electrons can able to jump from one orbital to another very easily. However, these are the two other possible reasons for electron shifting or deviation from AUFBAU principle apart from the one that is stable half filled or completely filled d orbitals. Let us calculate the number of elements in this period. The electronic configurations of outermost orbit of this period or fifth period is 5s, 4d, 5p. 5d is not there in this period as it has higher energy than that of even 6s orbitals. If we calculate the atomic orbitals, then 1 plus 5 plus 3, so total 9 atomic orbitals are there, so 18 electrons, and this implies 18 elements are there in this fifth period. The sixth period starts with the elements cesium, barium, lanthanum up to radon from atomic number 55 to 86. You can see at the bottom of the periodic table that after lanthanum, cerium 58 to lutetium 71, a total of 14 elements are arranged separately. These are known as F block elements, where the 4f orbitals are being filled up by the added electrons in these elements. They are also known as lanthanoids or inner transition metal elements. The general electronic configurations of the outermost orbital is n-2f1 to 14, n-1d0 to 1 and ns2, where n is 6. You can see here the electronic configuration of outermost orbit of sixth period. You can see 6s, 4f, 5d, 6p. But 6d is not there as it has higher energy than even 7s. As we know, the number of elements in the period depends on the atomic orbitals. So here, if we add up the atomic orbitals 1 plus 3 plus 5 plus 7, then it is coming to a total of 16 orbitals. So we have 32 electrons. So 32 elements are there in this period. The seventh period starts with the element francium with the atomic number 87 and it continues till the end, that is till unactium with atomic number 118. Just like sixth period, here also just after actinium, thorium with atomic number 90 to lawrencium 103, all total 14 elements are kept below the lanthanoids and are known as actinoids. These elements are also known as inner transition elements or F block elements, as the 5f orbitals are being filled up by the subsequent addition of electrons from thorium to lawrencium. In this period also, total 32 elements are present. So let us have a look into the general electronic configurations of the outermost cells of the elements in different groups in the periodic table. Hope with this periodic classification you have also learnt about the concept of filling of different orbitals. Thanks for watching this video.